Hi, I'm Jacob Stewart, and I'm here at the Midwest Astrochemistry Meeting, the 2009 version, and I'm going to present my poster on a mid-infrared continuous wave cavity ring-down spectrometer for acquisition of the high-resolution spectrum of C60. So we're interested in C60, buckmisterfullerene. This is a structure of it. C60 was originally discovered in experiments simulating carbon star outflow chemistry. So here we have a picture of a carbon star, IRC plus 10216, and you can see the shells of stuff, of molecules of carbon, carbon-rich material coming off the star. And the experiments originally were trying to simulate this sort of chemistry, what happened in this sort of environment. And that's when they discovered C60. So that implicates that there is C60 in this sort of environment. We'd like to be able to do an astronomical search for that, but in order to do that, we need a high-resolution spectrum of C60 to be able to look for it. So, down here, C60 has no permanent dipole moment, so you can't do microwave spectroscopy. The electronic transitions are weak or broad or forbidden, so we're left with vibrational spectroscopy, infrared spectroscopy. So there are 4 different vibrational modes. We've chosen the 1185 wave number vibrational mode because it coincides with an atmospheric window. And so the light source we use in this spectral region is a quantum cascade laser, which you can see here. Now the laser itself is this tiny ridge in between those gold pads there. And this is a centimeter scale ruler down here. So this is a very small laser. It's made up from stacks of semiconductor material that are specifically engineered to generate light at this particular wavelength. So if we move over here to our this is a diagram of our spectrometer. So we have our QCL, which is controlled by our computer, which controls the power supply and temperature controller. We tune the frequency of the QCL by changing the current in the power supply and the temperature at which the QCL is operated at. And that allows us to get about 20 wave numbers of coverage out of our QCL that we use. The light from the QCL is coupled via telescope into an acousto-optic modulator. So the modulator, when it's on, sends the light to our spectrometer down here. When the modulator is off, the light goes straight through and goes to our reference region where we verify the frequency of the QCL. So here we have our actual sample chamber where we produce the C60. And so we have an optical cavity made from 2 high reflectivity mirrors. And then on one mirror we have a piezoelectric transducer which allows us to change the length of the cavity. So when the length of the cavity reaches a resonance condition with the frequency of the laser coming in, we can see here when it's on resonance we get a spike in signal on the detector. Now we have a comparator that tells us when we reach a certain threshold to turn off the AOM, which turns off the light to the cavity, and we watch how the light comes out of the cavity, the decay of light from the cavity. And that's an exponential decay. The time constant of that decay is proportional to the absorption of any molecules inside of the cavity, and that's how we obtain our spectrum. This is what is known as cavity ring-down spectroscopy. So to actually produce C60 to look at, we have to use a high temperature oven because C60 has a very low vapor pressure. It's very much a solid. So this is a picture of our oven with our high-tech heat shield made from a turkey basting pan. We use that to reflect light from the oven back onto itself to minimize our losses from light coming off of our oven. When it gets hot, it glows nice and orange. So we operate this oven from 600 to 700 degrees Celsius, and that allows us to generate some vapor pressure of C60. We then run argon through the oven, through a pinhole to cool the C60 down in supersonic expansion. So we have tested our spectrometer with a test molecule, methylene bromide, that happened to fall in the frequency coverage of our laser. So this is our experimental spectrum up here, and a simulation that we did here with cold and warm components. The cold component comes from the supersonic expansion, but we also see some background gas that's at room temperature. And so the two of these added together gives us a fairly good fit to our experimental spectrum. And we can see that we're able to resolve individual rotational lines. We can see the P and Q lines are from methylene bromide. And so we're achieving the resolution that we'll need to be able to see the C60. So some of the problems we've been having are we would like to get more C60 into the gas phase, so we've been working on improving our oven, getting it from 600 degrees Celsius to 700 degrees Celsius to increase our vapor pressure by hopefully an order of magnitude. In addition, we've been working on improving the sensitivity of our spectrometer by decoupling the mirrors on they're rigidly attached to our vacuum chamber. We'd like to decouple those to eliminate problems with vibrations, with thermal expansion due to heat, the hot oven inside of the vacuum chamber. And so those are some of the areas we're working on to be able to improve the performance of our spectrometer so that we have a chance to be able to see C60. And that's our experiment.